Hello, Trig class. In this video, we're going to look at the inverse trigonometric functions: inverse sine, inverse cosine, inverse tangent functions. There's the different the objectives we're going to have for this video. The big thing we want to start off with is just the idea of the inverse trig functions. Now, one of the things that you learn in pre-calculus is the idea of an inverse function. And if you're looking at a graph, you know a function has an inverse if it always rises or always falls. So there's a function that's always rising. One of the things that you learn in pre-calculus is the idea of the horizontal line test, which says if a horizontal line only intersects a graph at a single point, then that graph is a graph that has an inverse. And that's why it has to always increase or always decrease. If it ever decreased and then turned and increased, it could not pass that horizontal line test. You know, a horizontal line would hit it in more than one place, and so it would have no inverse. And the reason why this is so important for trigonometry is all the graphs fail the horizontal line test. So, like, sine wave, it's going to fail the horizontal line test. A cosine wave, it's going to fail the horizontal line test. The tangent function, if you go outside of one set of asymptotes, it's going to fail the horizontal line test. So all the trig functions fail the horizontal line test. So it seems kind of weird to say the inverse trig functions because they're all periodic and therefore by definition will fail the horizontal line test. So the question then is, well, what do we do? How do we fix this? Because obviously there is some, because that's the name of this section. Well, what we do is we restrict the domain. We say, all right, the tangent function or the sine function only exists on this one region, and that is what we're going to use as the only outputs of the tangent function, or sorry, sine function. So what I've got here is this set of points. The dots there are everything that's within the little blue region, but it's like, a region on the axis. So this is like negative pi over 2 to, or sorry, negative 5 pi over 2 to negative pi over 2. And what we're trying to do is come up with what's the smallest region on the number line that I can use that contains all outputs of the sine function, meaning all the y coordinates. So it covers from negative 1 to positive 1. It covers the entire range of the sine function, but in the smallest window possible. And you can see that if I bring this right side in, I eventually get to a region that's small enough that it gets every value that sine can output between negative 1 and positive 1. And the smallest region I need is this width, right, which is just pi units. But what we also want to do is make this as close to the origin as possible when we're defining these functions. So like pi is not always, a width of pi is not always going to work. Obviously we don't get into the negatives there. All right, this one works, but again we could be closer to the origin if we actually center this at the origin. So there is the region that we bound the sine function to be between negative pi over 2 and positive pi over 2, and every value in the sine curve is hit. Every output is hit, and it's the smallest region as terms of distance from 0, smallest like an absolute value. So that's what we're going to restrict the sine function to in order to create something that passes the horizontal line test. Like I'm saying here, it doesn't pass the horizontal line test. It hits it over and over again. But if we restrict it to just that blue region, you can see it does pass the horizontal line test. So this function here, a horizontal line would only hit every point on that graph a single time. So that restriction of the domain creates functions that will have an inverse. So there's the definition. Y equals the inverse sine if and only if x equals the sine. So basically what happens here is y equals inverse sine. If I write that, if I take the sine of both sides of this equation, all right, the sine of the inverse sine kind of cancels out and leaves me with just x. And so I have x equals sine y. So that's how that works. Okay, but for it to be an inverse, again, one of the things you learn about inverses from pre-calculus is the domain. And our domain here is negative pi over 2 to positive pi over 2. That's the domain of the sine function that we've restricted. So there's that part of the sine wave. There's 0. This up here is at 1. That's pi over 2. The y coordinate is 1. This is negative pi over 2, negative 1. All right, and that's the origin, 0, 0. Well, the domain, negative pi over 2 to positive pi over 2, becomes the range. So you can see the y's for the inverse sine are bounded between negative pi over 2 and positive pi over 2. And the range, so for sine, it was negative 1 to positive 1. It was all y coordinates between negative 1 and positive 1. That becomes the domain. That becomes where the x values have to live for the inverse function. All right, let's graph this on a TI calculator. So I'm just going to go into y equals, and then y1 I'm going to do, instead of sine, I'm going to do second sine. Up above it you can see it says sine with a negative 1. That's the inverse sine function. That's not cosecant. That's inverse sine. So inverse sine of x. All right, I'm going to make my window go between, instead of negative 1 and positive 1, which is the domain of inverse sine. I'm going a little bit further out just to have a little more room. And then on the bottom and top, that is negative pi and positive pi that I put in there. Again, that's a little beyond the range. The range is negative pi over 2 and positive pi over 2. This is just to get a little bit of extra space so we can see all the key points there. And then my y scale is pi over 2. And my x scale will be 0.25. All right, so there's my graph. There's the inverse sine function. All right, so that is that blue curve that you're seeing there. If you press trace, what you're now seeing are coordinates where the x coordinate is a value that sine would output. So 0.718 roughly is my x coordinate. And the answer, that the y coordinate, the output that I get is what radian measure would I need to make the sine, the y coordinate on the unit circle, be around 0.718. And the answer is about 0.801. That radian measure, the sine of 0.801, is about 0.718. That's again that point that we're seeing there on the graph. So its input is the output of the sine function, and the output, the y's, are the angle required to produce that output. Now let's talk about the domain. It starts at negative pi over 2. Sorry, it starts at negative 1 and it ends at positive 1. And the angles that it can produce are negative pi over 2 and positive pi over 2. All right, recall on your unit circles, this is pi over 2 and this was negative pi over 2. Those are the angles that it can create. Well, that's just quadrants 1 for 0 to pi over 2 and quadrant 4 for 0 down to negative pi over 2. So you cannot, with inverse sine, you cannot get into quadrant 2 or quadrant 3. You can only land in quadrant 1 for positive values. Again, the y coordinates are what go in. So these y coordinates that are above the x-axis will produce angles, acute angles, that land us in quadrant 1. And then if you input values that are negative y coordinates, where we have to go down to hit the y coordinate, it's going to produce a negative angle that gets you there. It can't produce this angle that went all the way around into quadrant 4. It can only produce this angle that goes down in the clockwise direction into quadrant 4. And it cannot produce obtuse angles at all. So the output of the inverse sine function is a positive or negative acute angle. All right, so again, a unit circle is going to help a lot with this, kind of getting it down, especially when you're given these special values that we've seen already in the course. So this question wants to know where is, what's the value of the inverse sine of negative 1? And what that's asking us is what angle between negative pi over 2 and positive pi over 2 makes the y coordinate on the unit circle be negative 1. And the answer is negative pi over 2, because it has to be between those. The unit circle is going to say 3 pi over 2, but that's not possible with the inverse sine. It has to be between negative pi over 2 and positive pi over 2. So what makes sine negative 1 is the inverse sine of negative 1, and that angle is negative pi over 2 here. All right, again, you are going to need to know this value, or again, be able to create a unit circle on the fly. Watch the video where I show you how to make your own unit circle on demand if you're still struggling with coming up with these values. These values need to be not necessarily memorized. That's not a bad idea, but you should at least be able to derive a unit circle on demand. All right, in that little blue region, all right, negative pi over 2 is the only place that happens. There's the 3 pi over 2 that we see on the unit circle, but that is not in the output of the inverse sine function. So we can't get those values that are not in this squeezed little chopped off section of the sine function. So values don't exist. All right, find the exact value of the inverse sine of the square root of 3 over 2. All right, again, I can only be in quadrants 1 and 4, so I'm only looking over here. I'm looking for the square root of 3 over 2. There it is. So what value gets me that? It's pi over 3. Okay, once again, there's the square root of 3 over 2 for the y coordinate. So the sine is the square root of 3 over 2. But that angle is not in quadrant 1 nor in quadrant 4, so it can't be the one I'm looking for. So we got to make sure that we understand that restriction to quadrant 1 and quadrant 4 that happened. All right, so there is the question we're asking, but that angle has to be in that range. So once again, that's why it's pi over 3 here. All right, when these are not exact values that we know, like 60 degrees and 45 degrees, these are things that we would have to approximate with the TI calculator. So if I did an inverse sine of a third, I get approximately there. I'm going to hit second enter, change that third to a fourth, and I can get those two values. So you can use your calculator. You can use your calculator for the other one. Let me make sure you understand that. If I did the inverse sine of negative 1, there's that number, you know. Do you recognize it as negative pi over 2? If you do, great. If not, then you're going to either need to draw your unit circle or learn these decimals, or be able to just, you check it. I do what I just did. I can say that looks like one of the numbers that I know. Is it negative pi over 3? No, it's not negative pi over 3. And just guess a few times until I get to one of those. But you need to be able to use either technology or draw your own unit circle to help with these. Inverse cosine is very similar. The only difference is we would start off with the cosine function. And we can see that negative pi over 2 to positive pi over 2 is not going to work for cosine. We're not getting all the outputs. We're just getting the positive numbers. But if I do a little shifting between 0 and pi, I can get every positive and negative output. So still pi being the minimum width needed for this. Okay, it's just now they're all positives, meaning like all the angles are positive to produce all the outputs. So we're not going to get any negative angles here, but we do have, for the first time, obtuse angles. So the cosine function, the inverse cosine function I should say, is going to be that range between negative 1 and 1, okay, and it outputs pi all the way to 0, or 0 all the way to pi. So the domain is negative 1 to 1, just like it was for the inverse sine function. It's just now the range is a little different. We are outputting obtuse angles for the first time. All right, let's see it graphed on our calculator. So I'm going to go to y equals and clear out this inverse sine and replace it with inverse cosine. So second cosine, inverse cosine. I do need to change my window a little bit here. I'm going to still keep it negative 1 and a quarter, 1 and a quarter. But my minimum, I don't need to go down into the negatives here. I'm going to go slightly into the negatives just to show the x-axis. And then my y maximum, I'm going to make it 7 pi over 6. And then I'm going to make my scale be pi over 6. So there comes the inverse cosine function. So you can see it never dips down into the negatives. It starts off, if I hit trace, go as far to the left as I can go. There's that negative 1. I'll just press negative 1. Negative 1 pi. If I put in positive 1, I get positive 1, 0. I plug in 0, I get out pi over 2. Because, again, the output is what angles on the unit circle produce these inputs for the x coordinates. So let's look at what does 0 pi over 2 mean. Now we're looking at what angles make cosine be specific values. Cosine of the x coordinates. The x coordinate is 0 when the angle is pi over 2. So we're looking for angles, that's the output, when we give it specific inputs. So what angle makes cosine, the x coordinate on the unit circle, equal 0? pi over 2, or 90 degrees. All right, where is inverse cosine, or sorry, what is the inverse cosine of a half? Again, another way I can think of that is what angles between 0 and pi over 2 make the x-coordinate 1/2. So there's the x-coordinate, again, 0 and pi over 2. Now that's just quadrants 1 and 2. All right, quadrant 3 and 4 is not possible with inverse cosine. So we have to be in quadrant 1 and 2, and in quadrant 1 and 2, where are we equal to, 1/2. I'm thinking the square root of 2 over 2. So 1/2, and so that angle is pi over 3. So again, you can use the unit circle to find all of these special angle values, and then use your calculator if it's not a special angle. All right, where is cosine equal to negative square root of 3 over 2 between, again, 0 and pi over 2? So this is where everything, 0 and pi. There's where everything has to live. And I want to be negative square root of 3 over 2 for the x-coordinate. So there's my x-coordinate, negative square root of 3 over 2. So there's my angle, 5 pi over 6. So there's how we can use, again, the unit circle to find these. All right, inverse tangent, the next one, that is the same idea. If y equals the inverse tangent, that means the input, the x, is the output of the tangent function. All right, what's kind of weird and bizarre about the inverse tangent function is the original tangent function has vertical asymptotes at negative pi over 2 and positive pi over 2. And that will output all real numbers, meaning it will go down forever to negative infinity, it'll go up forever to positive infinity. So when we invert this, this does pass the horizontal line test. Everywhere in that red curve, it's only going to intersect the graph once. So everywhere in there, we pass the vertical line test. That means there is an inverse. And because of that property of we can flip the xy coordinates, the domain becomes the range becomes the domain, that means that all of the inverse tangent function lives between negative pi over 2 and positive pi over 2 as horizontal asymptotes. And the further I go to the right, the closer I get to pi over 2, but I never touch it. The further I go to the left, the closer I get to negative pi over 2, but I never touch it. And this is what we call a one-to-one function, meaning we never hit any y coordinate twice. And so the inverse tangent function, what's mind-blowing about it is it takes in all real numbers. So the domain is all real numbers, and it outputs something to negative pi over 2 to positive pi over 2, and it's completely unique, meaning it's one-to-one. And what does that mean? That means that the entire number line, all of them, all the numbers on the number line, fit in a window that's pi units wide. So let's make sure we understand what I just said. There's negative pi over 2 to positive pi over 2. That has a width of just pi units. And the entire number line, of which this is a part of, fits into that window. All numbers fit into the window between negative pi over 2 and positive pi over 2 by the inverse tangent function. That's what proves that we can do it. It takes in the yellow line, all real numbers, and it squeezes them in to the green line segment between negative pi over 2 and positive pi over 2. All right, finding a value. So inverse tangent, where is inverse tangent equal to negative 1? Well, because again, inverse tangent is defined on negative pi over 2 to positive pi over 2. It is quadrants 1 and 4 again. It's just these two quadrants. So where is inverse tangent equal to negative 1? So if it's a negative output, it's going to be quadrant 4. This is where we'll find negative output for inverse tangent, because again, tangent is the slopes of those line segments that connect the origin to the points, and that's negative slopes in quadrant 4. These are positive slopes. Okay, so since this is negative, that's not what we're after. All right, tangent is equal to negative 1 when sine and cosine have opposite signs. Remember, tangent is sine divided by cosine. So you can see here in quadrant 4, and that's where it has to be, they have opposite signs, square root of 2 over 2 and negative square root of 2 over 2. So that's the same thing, but opposites. So that's the angle, but we have to find the one that's coterminal with that. That's between negative pi over 2 and positive pi over 2. So that angle, instead of 7 pi over 4, is negative pi over 4. All right, once again, this calculator can help a ton with this. Second tangent, type in negative 1, hit enter. There's that. That's the number, but we have to understand that that's negative pi over 4. If I don't recognize it, I can play around with different exact values that I see on the unit circle until I get that number and kind of match it up, or you can just kind of think through it. Draw your own unit circle and think through it. All right, the second one is asking us where is it equal to negative square root of 3 over 3. So tangent is square root of 3 over 3 when the numerator is 1 for the y and the numerator is square root of 3 for x. 1 over the square root of 3 is the same thing as square root of 3 over 3. So there is my angle, and again it is in quadrant 1, so that's perfectly fine for inverse tangent. Again, if it's 1 or 4, that's fine. If it's trying to be in 2 or 3, we have some work to do, but 1 or 4 is perfectly fine. So that's our angle, pi over 6. All right, a couple of properties of the inverse functions, the inverse trig functions. If we have an inverse trig function on the outside and a trig function on the inside, then we get back x as long as x was between negative pi over 2 and positive pi over 2. If it wasn't, though, we're not necessarily going to get back to what we started with, which is, that's what it meant to be an inverse function, right? But it's only if we're restricted to this value. Inverse sine can only output things between negative pi over 2 and positive pi over 2. Same for inverse tangent. Inverse cosine can only output things between 0 and pi. So if we're starting in those regions, we'll remain in those regions. But if we start outside the regions, if this number is outside of negative pi over 2 to positive pi over 2, then this procedure will not get us back to where we started. We got to be careful when inverse sine is on the outside. All right, sine of inverse sine, though, we will get back to what we started with as long as we are within the domain of inverse sine, meaning we do have a number between negative 1 and 1 to start with. So that will always happen, but this one, when the inverse trig function is on the outside, we got to be careful. All right, so this first one, inverse sine of the sine of pi over 8. Pi over 8, and think about your unit circle. This all the way up is pi over 2. This is pi over 4. We're dividing by 2. So pi over 8, even though it's not a special angle, would be here. So it is in the domain between negative pi over 2 and positive pi over 2. It is in that quadrant 1, quadrant 4 region. So it's good. So the sine of that will give us some y coordinate. The inverse sine is the angle that produced that y coordinate, and we just saw it was pi over 8. So that is going to get us back to what we started. All right, but again, pay attention here. 5 pi over 8. Again, there's pi over 2. There's negative pi over 2. That's where you have to live for you just to be able to say these wipe each other out, and it's 5 pi over 8. Pi over 2, 1/2 pi, is smaller than 5 pi over 8. 5 pi over 8 is like over here. That's bigger. So that means we're not going to just get back to what we started with. All right, so the sine gives me this height, which happens to be, somewhere around there. And so there is an angle. This is the angle, that would get us there. But that's not possible for inverse sine. But this angle produces the exact same height on the unit circle. And so this is the angle that the inverse sine could produce. All right, what angle would that be? Well, it'd be whatever we have added to pi over 2 to get to 5 pi over 8 taken away from pi over 2. So just take 5 pi over 8, subtract pi over 2. That's just pi over 8. That's what that angle right there is. And now we need to take that angle away from pi over 2. So that's 3 pi over 8. So that is what inverse sine of 5 pi over 8 would be. It would return 3 pi over 8. So there's the work, and they're talking about that. That gets us there. So 3 pi over 8 is what we would output. All right, one of the things you can do on a question like that. So I have the inverse sine of the sine of 5 pi over 8. Close, hit enter. It gives me that. I don't recognize that number. It's not going to be pi over 2 because 3 pi over 8 is not a special angle. But what you can do is divide. If you're doing these inverse trig functions, divide by pi, change it to a fraction, and now stick the pi back in there. 3 pi over 8. So that's a little trick you can do for these inverse sine of the sine of an angle that's outside of our negative pi over 2 to pi over 2 range. All right, when inverse sine is on the inside and sine is on the outside, as long as this number is between negative 1 and 1, then this will always wipe each other out, and you'll just end up with that number. Okay, but if that number is outside of the range that sine can output, sine can't produce negative 2.5. So inverse sine can't take that in. So this is not defined. So you just have to be careful with when inverse sine is on the inside, you just have to be careful with what goes into it. As long as it's between negative 1 and 1, inverse sine and sine will just wipe each other out. But if it happens to go outside that range, you can't even do the problem. You can't even tackle it. Okay, you could try to type that in to your TI calculator. So sine of the inverse sine of negative 2.5, and it's going to give you what's called a domain error, which means that you didn't do anything wrong. It's just you can't plug that number into inverse sine. All right, it would also do that if you did the inverse sine of negative 2.5 without that sign on the outside. It's just you can't plug in numbers bigger than 1 and or lower than negative 1 into the inverse sine function. All right, and then the same thing for cosine. We just have a different window that we're working in. All right, inverse cosine. Pi over 15, that is between 0 and pi. So cosine and inverse cosine are just going to wipe each other out, and that's going to give me pi over 15. All right, inverse cosine. Inverse cosine has to take in a number between negative 1 and 1. If it does, if this number is between negative 1 and 1, and it is, then these are just going to wipe each other out and produce that input. All right, cosine negative 3 pi over 4. That is a negative number. Cosine, inverse cosine cannot output a negative. It can only output 0 to pi. So one of the things you can do on your unit circle, find where negative 3 pi over 4 would be. So there's 1 pi over 4, 2 pi over 4, there's negative 3 pi over 4. So that would put me down in quadrant 3. All right, inverse cosine is only defined in quadrants 1 and 2. So if this is where I ended up, just kind of follow it up, it would have the same x coordinate. So 3 pi over 4 is the angle between 0 and pi that would produce the same x coordinate you're seeing down here. And that's basically what this problem is asking. This gives me an x coordinate, and then this immediately turns around and says, what angle between 0 and pi would produce that same x coordinate? And you can just follow it up through the the x-axis all the way up until you hit the circle again, and there's our angle, 3 pi over 4. All right, inverse cosine again, it can only take in numbers between negative 1 and 1, and pi is much bigger than 1. So I guess then again would not be defined. So just be careful with inverse trig functions on the inside. All right, some of these problems will have you find an inverse function of a shifted or altered trig function. So this is 2 sine x minus 1. So that's the typical sine function. That's 0. That's 2 pi. All right, nothing's happening to x, so we're not shifting left or right. We're not changing or altering the period. It's just instead of this going up to 1 and negative 1, this is now would be going up 2 to negative 2. All right, but we're also shifting it down a unit. So the midline is going to move down, and so all of these points, and so we would shift to there to where now our max would be at 1 and our minimum would be down here at negative 3. So the domain is negative pi over 2 to positive pi over 2. The range is negative 3 is less than y is less than positive 1 because of that shifting. So when we do the inverse, when we find this inverse, this will become the domain, and then this will become the range. Right? That's the property of just inverse functions in general, not exclusive to the trigs. That's just inverse functions itself. They switch places. The x's and the y's do. So there's that property. We switch, instead of f of x, we call it y. We switch the x and y around, and then we start solving for the new y. This should have been an x. Sorry about that. And then we solve for the new y, and we get y, sine of y equals x plus 1 over 2. So that means sine inverse of x plus 1 over 2 is y. And then we go back to the inverse trig function notation. So there is our inverse function. Okay, the domain of that inverse function is negative 3 to 1. The range is the negative pi over 2 to positive pi over 2. All right, so range becomes domain, domain becomes range when we switch from function to its inverse. All right, we want to find the exact value of an equation that involves an inverse trig function. We just basically isolate the inverse trig function. So you can see this algebra is just isolating it. And then we use the definition of inverse sine, which is take the sine of both sides of this equation, and that's x. X is the sine of pi over 4 which is the square root of 2 over 2. So that's our solution. So we can use inverse trig functions to help us solve equations. We just have to make sure that the value right here makes sense, that we do have something that's in that range that the inverse trig function is defined to be in.